Okay, so in this part, let's go over the same type of work we did in the previous part, but involving now an epidemic model. And we're going to bring some earlier concepts, which I hope at this point those of you who take the class are familiar with. And again, remember the goal is to have textbook examples. That is, we simplify the models mathematically as much as possible and still maintain some of the main features we want to present. So remember, we always have a huge compromise on realism on these examples, just to emphasize how this analysis usually works. So I call this model a model with recovery and loss of immunity. So let's see why that's the case. We have susceptible, infected, and recovered. And we have a mass action law for the infection process from S to I. We have recovery that moves individuals from the infected class to the recovered class, but notice that we assume the recovery is not permanent or the immunity is not permanent. And then there's a transition back from the recovered class to the susceptible class back again. So for example, you have a disease like a common cold, which let's say provides just a limited amount of immunity. And then you lose that immunity by a certain rate. Remember the meaning of the reciprocal of the removal rate, because if you actually use real life data, that's what you should keep in mind. The reciprocal of R means the time spent in the I class, so you could call 1 over R the duration of the disease. If you say, for example, that the coronavirus, takes 14 days, this disease, then you could set 1 over R equals 14, and then you end up with R equals 1 over 14, right? If the duration of the disease is 14 days, let's say. And if you decide, of course, that the unit measure in the model is given by days. The duration of immunity, suppose that you're immune for, 3 months. That means 90 days. And then that gives you 1 over alpha equals 90, which means alpha equals 1 over 90, and so on. This is how the usually the data is fitted with the parameters based on what you know about the disease. And if you don't know, of course, you leave the parameter to vary, and then you come up with the conclusions. But remember, in the theoretical analysis, which we do typically, we don't actually need any real data if we are capable to actually analyze the model completely. Once we have the results, then we could basically see, given a certain data for the parameters, what the conclusion falls into. But ideally, you would have a model which is as general as possible, and you have a complete analysis without gaps, like in the previous case. So as I said before, we move on with examples that can be reduced to 2 equations. This one has 3 equations, but notice that if I add all equations, the derivatives cancel out. So that means the total population is constant or remain constant throughout the process. So the total population is, let's denote the total population by n, a constant. So that means S of t plus I of t plus R of t equals n. Be careful that when you go over this process, from this point on, all equilibria values need not just be between positive. They need to be between 0 and n, right? Because you are under the assumption that you start with n individuals, the sum of the S naught, Y naught, R naught is equal to n, so they should remain constant, which means any feasible value for the equilibrium point should be positive, of course, because these are population values, but it should also be less than n to fit this requirement. I mean, this constraint that the sum is equal to n. And then based on that, we can basically reduce the system to a 2x2. You can pick any 2 of these equations and replace the third variable with a difference between n. So let's say, for instance, I want to look at just the first 2 equations. That means I have to write everything in terms of S and I, which means R needs to be replaced by n minus S minus I. Remember, n is a constant, S and I will be the dependent variables. So this will be a 2x2 system given by minus lambda si plus alpha times n minus s minus I. And the second equation, lambda si minus ri. So now we can proceed with the 2x2 analysis, and like before, let's find first the equilibrium points. And just like before, we can see that the second equation factors easily. And that gives me two solutions, either I equals 0, or when lambda s minus r is equal to 0, s is equal to r over lambda. For each case, we go back to the first equation. So if I is equal to 0, plug it back into the first equation. That gives me s equals n. So one equilibrium point will be n and 0. I always specify the equilibrium point in the order SI, in the order of the equations given. Nothing special about the order, but you got to keep it up. I mean, if you establish a order from S to I, then keep that up throughout the analysis. Notice this will be called in our context the disease-free equilibrium. Because if you approach it, if this becomes convergent, if it attracts solutions, if it's stable, in other words, that means you approach a state in which the disease disappears. So then everybody will be susceptible at that equilibrium value. N is the total population, and if S is equal to N, that's essentially the happy outcome when everybody ends up being susceptible in the long run. Then the second possibility, if S is equal to R over lambda, going back to the first equation, let's plug it in. And we're going to solve for I eventually, right? So let's factor that, let's say alpha n minus alpha times S, which is again R over lambda, and then minus alpha I, which I'm going to bring it to the right-hand side. So lambda cancels, and I'm going to bring minus Ri to the right-hand side as well. So we have alpha quantity n minus R over lambda equals alpha I plus Ri. Let's do a little bit of extra algebra here. Factor out I, and then finally the value of I is alpha lambda n minus R over lambda R plus alpha. All right, so let's write it on the next page. I think I'm going to copy the system just to have it in front of us. It's not that long. And the equilibrium values that we just found. The disease-free state and 0. And the other one, which is going to be called the endemic state. So S was R over lambda, remember? Alpha quantity lambda n minus R over lambda R plus alpha. The endemic state. Because at this equilibrium point, the conclusion, if it's become stable, the conclusion is that the disease establishes itself in the population. So you approach the limit, and in the long run, you don't get rid of the disease because the infected class will approach a positive constant. And speaking about positive, remember always the feasibility condition. The endemic state is feasible or biologically feasible or positive. In my case here is if lambda n minus R greater than 0. So we need to have that condition for this to be biologically meaningful. Now, there is another biological, see, normally this is going to happen by default here, but in a more complicated model, you have to take into account that as well. because sometimes you can have surprises in terms of feasibility. See, you always have to remember that you came up from an SIR model, right? And remember, R is n minus s minus I, which, again, that guy should be also positive. We reduced the system to a 2x2 system, but remember, you always have a third variable, which is the difference between the total population and s plus I. And if that is not positive, then again, the equilibrium is not feasible. So you could have, and that could be sneaky, not here, but in more complicated models, could be sneaky because you could have S positive, I positive, all good, but when you check the third equation here, this could be negative, which means the whole thing is invalid, right? I mean, the equilibrium is not possible. So what is that for the disease-free state? All is good, right? Because in that case, you have n minus 0, which is 0, so that's fine. The recovery class is also 0 if everybody is susceptible. But here you'll have to also check for the endemic case whether R at the equilibrium value, which is n minus s of, which is R over lambda minus alpha lambda n minus R, lambda R plus alpha, whether that's positive or not. So we could do this by hand. Again, this is the place where Maple really comes handy, because you could do this with Maple quickly. You could simplify this expression. Let's do it by hand. So you multiply n by lambda R plus alpha minus R plus alpha. Do this by hand and pause and check with me later. You don't want to rush. So lambda n R and alpha. Some of the terms will cancel here. That's why I'm going to expand them all first. And I should say that with a little practice, you can anticipate some of these cancellations. I forgot a lambda here, right? So lambda n R plus lambda n alpha. So lambda n alpha will cancel, alpha R. And if you look carefully and you pull out R, the recovered class becomes R quantity lambda n minus R over lambda R plus alpha, which is also positive if lambda n minus R is positive. So there's no surprise here. Notice that the feasibility condition for I ends up being the same feasibility condition for R. So we're good to proceed with these equilibrium points under the, again, the condition that when we move on to the endemic point, the endemic case, we need to have this condition for the for it to be biologically meaningful. So with that in mind, let's move on with the Jacobian analysis. So let's take a look at the equations. So the Jacobian in S and I, so we have partial S. Partial S, remember everything else is a constant except S. So minus lambda I. Here you pull out alpha and the derivative of the inside is minus 1. N is a constant by default. You do partial S, so I is treated as a constant. So that's minus alpha. Then we do partial I. That's minus lambda S. Again, minus alpha. Second equation, partial S is lambda I. Partial I is lambda S minus R. All right. Let's plug in the disease-free equilibrium. Always easier to analyze. So if I plug in 0 for I and N for S, this becomes minus alpha minus lambda N minus alpha. 0, always a good sign. When you have a 0, makes everything easier. And lambda N minus R. Again, crucially important to remember, if the determinant can be factored, start with it. Okay? Right now, again, you're looking at the conditions determinant positive, trace negative. Under what conditions both of these inequalities hold? Because of this 0, the determinant, notice, is minus alpha lambda N minus R. When it's positive, that implies lambda n minus r less than 0, right? Negative times negative should be positive. But if that's the case, then automatically the trace, which is the sum of minus alpha and lambda n minus r, automatically is going to be negative if lambda n minus r negative. So once again, we have a single inequality deciding the stability. So we say that n0 is stable if lambda n minus r less than 0. And because of the meaning related to, of the epidemic reproductive meaning, let's rewrite this in terms of something less than 1. So move r to the right, divide to the r, and that's the condition of stability for the disease-free state. We're going to go back again later to the discussion of why this, in terms of the epidemic, is more meaningful. We talked already about the epidemic reproductive number, but I'll repeat that discussion shortly after I'm done with the analysis. For now, let's just use again our common sense. What does this state basically? It states that the infection rate, if it's less than some quantity, let's say you basically rewrite this as something like lambda less than something, right? Lambda is the infection rate. Does it make sense to say that if the infection rate is lower than a certain value, does it make sense to say that the disease disappears? Yes, it makes sense. If the inequality would be the other way around, then you would have a problem that you need to explain, either a computation mistake or some weird stuff in the model. But right now, of course, the result makes perfect sense, because the lower the infection rate, the greater the chance for the disease to disappear. So with that in mind, let's move on to the endemic state. We're going to plug into the Jacobian the endemic equilibrium. So remember, what I plug in is, r over lambda for S, and alpha lambda n minus r over lambda r plus alpha for I. So the Jacobian in that case is going to be obviously a little bit more complicated. Minus lambda times I minus alpha, if you got the minus alpha, minus lambda times S minus alpha, lambda I lambda S minus R. Okay, we're still good in terms of stuff to do by hand here, because, and that's why the model is easier to analyze, because one corner will be 0 again, as you'll see. So let's simplify this a little bit. It's very important not to combine the terms until you need to, or if there is an advantage to it. This is why when you use Maple, you should use your brain as well all the time, because if you let Maple do whatever it wants to do, like for instance simplifying, when you don't need to, when you could use your brain in a more efficient way, Maple becomes a liability actually than just a helping tool. And let's see, and then this becomes 0, this corner. All right, so let's 1 second. Want to double check something before we move on. All right. Okay, so we have a corner 0 here. At this point, we could still start with the determinant, but you could also notice that under the conditions of feasibility, the trace is always negative. In fact, let's actually ponder a little bit, because this is extremely important when I said Maple can be a liability if you're not paying attention. Maple doesn't know by default what are the conditions on these parameters. But you already know, as I said before, that you are under the condition that this is biologically feasible. So all this game of analyzing the endemic state is under the condition that lambda n minus r is positive, otherwise it would make sense biologically. But let's actually watch and let's stare a little bit at the trace, right? So the trace is this corner plus 0. So the value of the trace is just given by this entry over here. If I'm under the condition lambda n minus r is positive, watching all the other parameters and the negative outside, we can clearly see the trace is negative by default, or coming from this condition. If I actually simplify this with Maple, the terms will be combined and it won't be clear what the sign of this corner is. Because it'll be like plus alpha r minus this, and then maybe with some other guys here, who knows? I mean, it could be a mess, you know, it's, you know, a variable salad here, essentially, if I combine it mindlessly. Right now, I can see clearly it's negative because of this guy being positive. So I have this condition established anyway. The determinant is 0 times this left corner minus r minus alpha, this corner, times alpha n minus r over r plus alpha. So the determinant is, if I cancel here the minus, is given by this, which clearly is positive if lambda n minus r is positive, which again is established. So again, the endemic equilibrium, so the endemic state is stable if it exists. Once the biological feasibility condition is established, then we know that we can show that it's stable automatically. So how do we rewrite this in terms of something compared to 1? Just like before, move r to the right. So the condition of stability for the endemic state is lambda n over r greater than 1. All right, so the outcome of our analysis, or the stability analysis outcome, is that we have the disease-free equilibrium stable if lambda n over r less than 1, and the endemic state stable if lambda n over r greater than 1. So the entire stability condition is determined by this quantity, which is called R naught, you know, the epidemic reproductive number. Which in my case splits the model into two possible outcomes. If it's less than 1, the disease goes away. If it's greater than 1, the disease persists. Again, most of the basic models, like I said before, will have this essentially two outcomes possible. More complicated behaviors can happen, but in general, in the most basic models, that's what you would expect to have. So I'm gonna comment a little bit on the meaning of R naught, and the reason again why we compare it to 1. In fact, let's actually write it down on a separate piece of paper, because I want to comment on some other aspects related to the parameters as well. So what is the interpretation of R naught? Typically R naught, again, and I mentioned before in another situation, in other models, it's the number, it's kind of a word salad here, but number of secondary infections caused by an individual infected in a healthy population. It's important to know this stuff because this is how you understand the limitation of using R naught actually to predict what happens during the epidemic. It's really a measure of what happens actually in the early stages of the epidemic. So if you look at our values here, you know, lambda n, so 1 over r is the duration of the disease. As I mentioned before, And lambda n, if you imagine that everybody is healthy, this is essentially the number of infections caused by just one individual. There's no I here, right? So, because remember, in the infection process, you have lambda Si. So imagine that essentially S is replaced by N, I is replaced by 1. This is why the R naught measures the force of infection coming from just one individual, or like you noticed in the news when they talk about patient 0. Of course, that's an idealization essentially, because there's no, it's not like there is a single one. There might be maybe 2 at the same time coming up in the community, but basically, if you analyze what happens with the start of the epidemic, you imagine you have just one infectious person popping up in the community that's healthy otherwise, and you look at the impact of that individual during his infection time. That matters, right? So it's multiplied, this is per unit of time, and then when you multiply by the duration of the disease, then you basically estimate the number of infections during while that person is infected. So that's why it's called epidemic reproductive number, because if this number of secondary infections exceeds 1, that means each new infection is replaced by more than itself. Let's say R naught is equal to 2, one infectious individual causes 2 infections, in turn this causes 4 infections, then 8, then 16, and so on, and which is the reason why you would expect in the beginning the infection to increase exponentially. But this is just the early stages of the epidemic, because remember, as the process goes on, first of all, each infectious individual doesn't meet just healthy people, so you're going to have fewer opportunities of infections as more people are infected. And of course, the big unknown is the behavior modification of people, right? I mean, you have masks, you have control measures, and so on and so forth. So that there's a very big limitation, and one should be very careful not to basically use the R naught to basically predict the total number of people infected in the long run. That's just a rough estimation in the beginning of the epidemic. Now you may wonder what happens to the immunity. Why does alpha doesn't play any role? It's not always the case that all parameters play a role in the R naught. So notice whether we have an epidemic or not depends just on the duration of the disease and the infection rate. Does alpha play a role, or the duration, the loss of immunity? Yes, it does, but more like in terms of how many people are infected. So if you go back to the endemic equilibrium point values, so we had R over lambda for S, alpha lambda n minus R over lambda R plus alpha, and I think, let me see, because I computed that before, the recovery class was R lambda n minus R over lambda R plus alpha. Sometimes it might be, so that's I and that's R. It might be useful, for instance, to estimate the impact of some parameters, right? So alpha, remember, is the loss of immunity rate. How fast you move from the recovered class back into the susceptible class. So you could do some limiting behavior. You could say, okay, to kind of gauge the effect of alpha, what happens if you have a huge loss of immunity? So let's say alpha goes to infinity, which is like no immunity, basically. Like once you move to the R class, you leave it immediately. It's like an infinite removal rate. Oops, it's out of range, sorry about that. So alpha goes to infinity, it's like an instant removal rate from R to S. Well, it shouldn't be a surprise that if you actually take the limit as alpha go to infinity, it shouldn't be a surprise that R goes to 0 in that case, right? I mean, you basically have no recovered class, and this could actually act like a control check, because if R doesn't go to 0, if alpha goes to infinity, again, we maybe made a mistake here. So notice if I take the limit, the top doesn't depend on alpha. If alpha goes to infinity, this is just a fraction that goes to 0, as it should. If you remember limits from calculus 1, when alpha goes to infinity, you have alpha on both sides of the equation of the fraction. So the limit is the ratio of the coefficients of alpha. So if alpha goes to infinity, the limit is lambda n minus R over lambda. which is n minus r over lambda. So you could basically estimate kind of that the maximum possible of I if no immunity happens. Let's say you don't know exactly what level of immunity you have in the population, and that's basically kind of the worst outcome in terms of the equilibrium value for the infected class, if alpha goes to infinity. So it plays a role, but not in the epidemic reproductive number. And with that, I think it's okay to stop at this part. We're going to go over at least one part. I'm not sure yet. Probably I'm going to make 2 parts just to not make it too long a video, in which I'm going to comment on how you deal with some of these results using Maple or something similar. So stay tuned for the Maple part.